Hello and welcome to the latest and greatest episode of Mr. Martin Sits Alone in a Room Talking to an iPad Screen. Today, we'll talk about energy and work. But before we do that, I want to talk a little bit about money. So overall, what is money? To me, it's not really a thing you can hold. Like, yeah, I can pick up this dollar bill, and everyone agrees that I'm holding a dollar. But really, it's just kind of a piece of paper with some special ink on it. I can't hold the idea of a dollar. Instead, the society collectively agrees, yes, that piece of paper is worth $1. And then I can do all sorts of things with it. I can store it, I can put it in the bank where I will save it for later, and I can convert it pretty much anytime I want. I can transfer it to a different currency, or I can transfer it for goods. So I can change the form that I have my money in, but I can't ever actually create or destroy the money without breaking the laws of the United States government. So that's no good. Well, energy is kind of similar. Energy is a property of matter. I can't hold a joule of energy. But I can look at something moving and tell you how many joules of energy that thing has, just like I can look at a dollar bill and tell you how many dollars it represents. It can't be created or destroyed without breaking the laws of physics. But it can be transferred from one form to another. So, just like I can transfer the big bucks I get as a public school teacher to a yacht, a private yacht, I can transfer forms of energy from one to another. But I'm not going to introduce new energy, I'm not going to take away energy. I'm just going to possibly move it elsewhere. The first form of energy we're going to talk about is kinetic. When you think the word kinetic, that's basically any sort of motion. So this is the energy of motion. It depends on a couple of things, the mass and the velocity of the object. And you end up with an equation of the kinetic energy of an object is just 1/2 times the mass times the velocity squared. Now here's something exciting about that. Kinetic energy is a scalar, not a vector. And that's kind of exciting, actually. Simply because with vectors, you have to worry about direction, you have to worry about an x component, a y component, you got to worry about an angle, and there's none of that here. A scalar is just a value. So essentially, I'm just taking the value of the velocity, the value of the mass, and running it through the equation to just get a raw value of energy. That actually makes these problems a lot easier to deal with than what you all have just been doing. Now another form is potential energy. For this one, objects don't even necessarily need to be moving. All that matters is, are they in some sort of a force field, like a gravitational field or an electromagnetic field. We'll talk electromagnetic way later in the spring semester, but for now, you can think of it as just stored energy, kind of like me putting money in the bank, and it just depends on the height on Earth. So the higher up I get away from Earth, the more potential energy I have. And you can look at it this way. The potential energy, which for some reason is often characterized with the letter U, U equals mgh, my mass times the local acceleration due to gravity on Earth, that's 9.81 meters per second squared, times h, the height in meters. So, as a brief example of this, let's look at a couple of Mr. Martins side by side. In the first instance, I am just standing on the floor next to my lab table. A little bit later, I climb up onto my lab table. And now that I've climbed up on the lab table, even though I'm doing the same thing, staring silently at the camera, I've got a lot more energy in the second instance, simply because there's a lot more chance of me transferring that energy to kinetic if I were to fall off the table. In fact, I can compare the energies by looking at the differences in my height. In each image, if I just pick the location where the top of my head is, the difference in its elevation, I'm just going to call delta H. And that change in height is going to be equivalent essentially to the change in the total kinetic energy, or sorry, potential energy that I'm feeling, where potential energy is my mass times 9.81 times my height. Cool. So from the two equations that we've gotten so far, what are the units of energy? Well, let's look at the kinetic energy equation. The kinetic energy is 1/2 mass times velocity squared. If I go to base units, which you should pretty much always do, that means I'm left with some unit of kilogram times meters per second. And that whole thing is squared, since the velocity is squared. So I end up with a kilogram meter squared per second squared. Cool. Well, on the other side of the aisle, let's look at potential energy. I've got mass times the acceleration due to gravity times a height. So I've got kilograms times meters per second squared, that's the unit of 9.81, times the height of meters. And look at that, it all comes out to kilogram meters squared per second squared. Now we use energy a lot, and to continuously repeat kilogram meter squared per second squared, kilogram meter squared per second squared is a lot. So instead, we look at it in terms of joules. 1 joule is 1 kilogram meter squared per second squared. Or another way to look at it is just 1 Newton per meter, since from F equals ma, a Newton is just a kilogram meter per second squared. The only difference is between force and energy is I'm missing this extra factor of distance, and that'll actually play into work in just a second. But before we get to work, I want to talk briefly about conservation of energy. If I've got an isolated system, basically a series of objects that can interact with one another, but not with other things in the universe, then energy is never created or destroyed, it's only transferred. So as an object falls, its potential energy is converted over to kinetic energy. But during the fall, the total energy stays exactly the same. The total energy being kinetic plus potential. Kind of another way of looking at that is my initial kinetic energy plus my initial potential energy equals my final kinetic energy plus my final potential energy. Or at any point, I could say that 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared plus mgh2, where I start with some initial condition at point 1, and at point 2, somewhere in the course of my motion, it doesn't even have to be at the end of my motion, but somewhere in the course of the fall, I get to height 2. I can solve for what speed I am at any given height through this. The nice thing is when we're only dealing with gravitational potential and kinetic, the mass almost always cancels out of every term, which is pretty cool. So all that matters is your speed, your height, and the acceleration due to gravity of whatever planet you're on. And that's pretty nice. Now this works when you're under a conservative force like gravity. But if something from the outside of the system comes in and starts to push you, that thing is said to be doing what's called work. It's just a change in some object's energy by some outside force coming in and moving you around. Now, notice how it says a change in some object's energy. It's still not a change in the total energy in the universe. I can't change that. What I can do is take energy from one object and move it to another. Just like I can steal money from any of you at any given time. I could have positive work if I add energy to the system, or I could have negative if I take it away. One way to find work is F times D times cosine theta, where F is the force on the object from something else, D is the distance over which the force is applied, and theta is the angle between the direction of the force and the direction the object moves. So I don't necessarily, I could be pulling up and to the right on something, and it just moves horizontally. If there's an angle theta there, that's that. Now a lot of times, the force at which I pull will cause the object to move directly in the same line. So theta would be 0 degrees, and the cosine of 0 is just 1. So in those instances where a force is in a certain direction, the object moves in that exact same direction, I would just get that work equals force times distance. But sometimes the force pulls one way and the object moves a slightly different way. That's where the cosine of theta comes in there. Not only that, you can just find work as your change in energy of the object. So look at the object's total energy, kinetic and potential, then ask how that has changed as a result of the force. I could find the work done as simply the change in kinetic energy, so the final kinetic energy of the object minus the initial kinetic energy of the object, or something like that, if I speed it up. Not only that, since I can find work two different ways, a change in energy, so ask yourself, what was the initial energy, what was the final energy, what's the difference? Boom, you've got the work in joules, since it would have the same unit as energy, since it's just the change. Or it could be force times distance times cosine theta. Since I've got those two ways of doing it, I can solve a lot of problems by simply setting my change in energy, find what that change is in joules, set it equal to the force times the distance traveled times cosine theta. And that's what a lot of these energy problems boil down to, or at least these work problems. So the problems you will be facing soon are conservation of energy. Can you set 1/2 mv squared plus mgh at one point equal to 1/2 mv squared plus mgh of another? And can you find your overall change in energy, set it equal to force times distance times cosine theta, solve for either the force or distance or the change in energy? So that's what we will be exploring in class soon. Until then, have a great, again, insert time of day that you are watching this video. Farewell.